An international team of scientists, including NYU Abu Dhabi researcher Nikolaos Georgakarakos and others from the US, Japan, and China, led by Jian Li from Nanjing University, has developed new insights that may explain the numerical asymmetry of the L4 and L5 Jupiter Trojan swarms, two clusters containing more than 10,000 asteroids that move along Jupiter's orbital path around the Sun. Hello and welcome to KYC News. Please don't forget to subscribe and hit the bell icon. For decades, scientists have known that there are significantly more asteroids in the L4 swarm than the L5 swarm, but have not fully understood the reason for this asymmetry. In the current configuration of the solar system, the two swarms show almost identical dynamical stability and survivability properties, which has led scientists to believe that the differences came about during earlier times of our solar system's life. Determining the cause of these differences could uncover new details about the formation and evolution of the solar system. In the paper, Asymmetry in the Number of L4 and L5 Jupiter Trojans Driven by Jumping Jupiter, published in the journal Astronomy and Astrophysics, the researchers present a mechanism that can explain the observed number asymmetry. We propose that an outward, in terms of distance to the Sun, fast migration of Jupiter can distort the configuration of the Trojan swarms, resulting in more stable orbits in the L4 swarm than in the L5 one, said Li. This mechanism, which temporarily induced different evolution paths for the two asteroid groups that share the orbit of Jupiter, provides a new and natural explanation for the unbiased observation that the L4 asteroids are about 1.6 times more than the asteroids in the L5 swarm. The model simulates the orbital evolution of Jupiter, caused by a planetary orbital instability in the early solar system. This led to the outward migration of Jupiter at a very high speed, a migration that the researchers hypothesized was the possible cause of the changes in the stability of the nearby asteroid swarms. Future models could expand on this work by including additional aspects of the evolution of the solar system, which could depict it with improved accuracy. This could include simulating the fast migrations of Jupiter at different speeds and the effects of nearby planets. The characteristics of the current solar system hold as yet unsolved mysteries into its formation and early evolution, said Georgakarakos. The ability to successfully simulate an event from an early stage of the solar system's development and apply those results to modern-day questions can also be a key tool as astrophysicists and other researchers work to learn more about the dawn of our world. Jupiter is by far the largest and most massive planet in the solar system. And befitting a world named for the Roman king of the gods, Jupiter has an impressive entourage. It includes a set of faint and dusty rings, 67 known or suspected moons, and two swarms of asteroids that precede and follow the planet in its orbit. These last are the Trojan asteroids. For all we've discovered about Jupiter, its moons, and even its gossamer rings, we know precious little about the Trojans. Pioneers 10 and 11, the two Voyagers, Galileo, and Juno have all returned a wealth of data about the Jovian system. Until now, though, the only way to study the Trojans has been from afar, with ground-based and Earth-orbiting telescopes. That's about to change. In 2017, NASA gave the go-ahead for a new Discovery-class robotic mission set for launch in 2021. The space probe will visit and explore 6 different Jupiter Trojans and a main belt asteroid for good measure. So little is known about the Trojans that the data will certainly revolutionize our understanding of these ancient bodies. What the spacecraft uncovers could confirm some current theories of the solar system's early evolution or turn it all upside down. The first official Trojan was discovered February 22, 1906, by German astronomer Max Wolf. 8 months later, August Kopf discovered a second asteroid near Jupiter's L5 point. The following February, Kopf found a third, this one near L4. The Trojans may not have formed in Jupiter's current orbit around the Sun, but it's unclear exactly where they came from. An artist's impression of the Trojan asteroids, which share the same orbital path around the Sun as gas giant Jupiter. The Lagrangian points around an orbiting body are special points in space, where the gravitation of the Sun pulling in and the centrifugal force of our motion flinging out act to balance each other out. These regions around the Earth are very useful for spacecraft. Advertisement. For example, the Soho Solar Observatory has been parked in the L1 Lagrangian point between the Sun and Earth, and the WMAP probe that mapped the remnant heat from the Big Bang is at L2 beyond the Earth. Artist's illustration of NASA's WMAP mission mapping the cosmic microwave background. Credit: NASA/WMAP Science Team. Artist's illustration of NASA's WMAP mission mapping the cosmic microwave background. Credit: NASA/WMAP Science Team. There are also Lagrangian regions situated 60 degrees leading and trailing any massive object in its orbit. In Jupiter's case, its L4 and L5 regions are each populated by a swarm of asteroids. They are known collectively as the Trojans, with the largest of them named Agamemnon, Achilles, and Hector. The origin of the Trojan asteroids. Illustration of the Lucy mission's 7 Trojan asteroid targets. Credits: NASA's Goddard Space Flight Center. These Trojan asteroids aren't thought to have formed at $5.20, the distance of Jupiter's current orbit from the Sun, but it's unclear exactly where they came from. Were they originally icy planetesimals from beyond Neptune, scattered and then captured by Jupiter during a period of orbital instability early in solar system history? Or perhaps Jupiter collected them when it formed further out, before migrating inward towards the Sun. Clues to the origin of the Trojans can be provided by studying the distribution of their sizes and surface characteristics. Katomi Yuhata, at the Department of Planetology, Kobe University, Japan, and her colleagues surveyed the Trojan asteroids in the L5 Lagrangian region, trailing behind Jupiter in its orbit. They used the Hyper-SuPrimeCam (HSC) fitted to the 8.2M Subaru telescope at the Mauna Kea Observatory on Hawaii. They found a total of 189 L5 Trojans down to an apparent magnitude of plus 24.0, corresponding to objects with a diameter of between 2 kilometers and 10 kilometers. As expected, the size distribution of these objects follows a power law. There are exponentially more smaller bodies than larger ones. They also showed, by comparing with an earlier study the team had conducted on the L4 Trojan swarm, that this size distribution is the same for both Trojan swarms, indicating that they came from the same primordial population. In total, Yuhata calculates that there are about 260,000 Trojan asteroids bigger than 1 kilometer trapped in Jupiter's L4 and L5 Lagrangian regions, roughly 10 times fewer than there are in the main asteroid belt. Interestingly, though, Yuhata discovered that in the L4 swarm ahead of Jupiter, there are about 40% more asteroids with a size larger than 2 kilometers than there are in the L5 Lagrangian region trailing behind the planet. This asymmetry in the L4 and L5 populations supports the theory that the Trojans were captured by Jupiter as it formed further out in the solar system before migrating inward. An artist's impression showing the Lucy spacecraft flying by a Trojan asteroid near Jupiter. An artist's impression showing the Lucy spacecraft flying by a Trojan asteroid near Jupiter. Credit: Southwest Research Institute. The Trojans are a fascinating category of objects, and studying them close-up promises to teach us a great deal about the origin of small icy bodies from further out in the solar system. Luckily, there is already a space probe en route to explore asteroids in both of Jupiter's Trojan swarms. The Lucy probe, launched in October 2021, will fly by 4 L4 Trojans, as well as a main belt asteroid on its way out, before arriving in the L5 swarm in 2033.
Yeah.